this is a screencast I'll be giving at Euro in Vilnius from the 8th till the 11th of July, as well as Auras in Twente from the 15th to the 20th of July. So the title of the talk is a game theoretical approach to the EMV ED interface. The EMV is meant as the emergency medical vehicles, so ambulances and such, and the ED is the emergency department, so accident and emergency department. So this talk, I'll briefly talk about the motivation of the work. I'll describe a single hospital game, then a non-cooperative game between two hospitals, and then I will conclude. But I must say that it will not be completely linear, and whilst I was doing this research, a particular thing caught my interest, well, I thought was particularly interesting, so I'm going to take us on a slight detour before I get to the main crux of the talk. So this is a hospital. You might argue that it's not the normal hospital that you see, and I would say you're right. It was missing a long waiting list of people trying to get in, but the hospital's full. And in general, what happens is that operational research turns up, operational research, management science, turns up, and the first thing OR will do is get rid of the queue. And once the queue's gone, it might make the hospital look a bit nicer, give it a new lick of paint, make the sun shine, and perhaps even plant a tree. So OR is very good at that. It's obviously a parody of what happens, but OR's at the point now where it's good at improving one particular aspect of an entire system. But the point of this talk is mainly to show that is not necessarily enough. This is a very simple model of a hospital. So it's a queuing theoretical model where we have three types of patients arriving. Elective patients that go straight to a ward, patients that walk in, and patients that arrive via the emergency services at the emergency department. The emergency department and the ward are both modeled as MMCQs, so patients arrive randomly, their service time is random, according to the service rate μD, and they have a particular number of servers, little c, and in this case big C minus little c. And patients transition from the emergency department to the ward, only a certain proportion of them. So a proportion P of patients, once they're done in the emergency department, they leave. They don't need to be admitted to the ward. But the patients that don't, they go on to the ward. And the problem that this particular simplistic model of a hospital has is, given an entire amount of resources, big C, so these could be beds, how many of those beds do I put in my emergency department, and how many of those beds do I have in my ward? But the question is, I'm trying to maximize throughput. So given these arrivals, I'm trying to get as much patients through the hospital per unit time, and that's the expression there, where these probabilities are dependent on the arrival rates and the emergency rate and the service rates at each of these two units. We then associate a routing game with the emergency medical vehicles, so with the ambulances. So we say, all right, the ambulances arrive, so in other words, there's a patient that arrives via ambulance at a particular rate, big lambda, and then the ambulance has a decision to make. It can either go to the emergency unit, where the cost associated is given by this formula, which is the waiting time, the expected waiting time in an MMCQ. In other words, how long will the queue be in the emergency department? And beta. So that's another cost. So that can just be taken as a constant. So for example, that can be 20 minutes. So the emergency units will, the emergency vehicles will fill up the emergency department up until the point at which the wait time is 20 minutes. In Wales, for example, the guideline is that the wait should be no longer than 20 minutes, but often ambulances are seen waiting with a patient outside of an emergency department for much longer. So this model does not allow the emergency unit to the ambulances to wait longer than a particular value beta. So the assumption is that the ambulances go elsewhere if that occurs. Now, this graph, what it shows is two things. So in red, that red line is the best response of the ambulance, of the emergency department. So if we have an arrival rate of for these particular values that I've taken, arrival rate of 8 patients per unit time, then the emergency department should have about 25 resources allocated to the emergency department. The hospital should allocate 25 resources to the emergency department as opposed to the hospital. And then what we have here is for various values of beta, so various values of what this target could be. As the hospital allocates more resources to the emergency department, we see that the number of patients that will be arriving at the emergency department increases. So the intersection of the red line and any other line, and any other these dots, is an equilibrium, is a point at which there's no implication to, no incentive to deviate from the strategy. So what you first of all see is that apart from these green dots, which is a value of beta equals 0.3, there is actually no equilibria. All here there is no equilibria, so the equilibria is actually very, very low. Now, all that implies is actually that the emergency department shouldn't, best response is to not put many, to not have many beds, and the emergency unit is to not send many patients. So of course that, in the grand scheme of things, means a lesser throughput. But now for the slight deviation I discussed when outlining this talk, what you might find interesting is that these dots here, so the best responses of the EMVs, almost appear linear, right? And that's what we're going to take a slight look at. So those dots are solutions to the routing game. And solving the routing game is equivalent to solving this equation. So that the wait in an MMCQ, where the service rate is mu and the number of servers is C, must be equal to some value beta. And so what we found is that X is in fact linear in C. Well, sorry, not that we found, but looking at that graph, it looks like X is linear in C. So I threw my computer at that and tried to see if it was true. And the answer is that it's almost true. So for given mu, C, and beta, we have that if we take X to be given by this formula here, which is in fact linear in C, then the distance from beta is very low, and in fact, as the service rate increases, it decreases. So it gives us that this equation is actually almost an answer. It's almost linear. But what we also see is, and in fact, if we choose our parameters, and of course the scale is irrelevant, so we can make mu as big as we want. If we choose our parameters in such a way that mu is quite large, then this is almost an exact solution. And in fact, for C equals 1, and that should probably be a bigger or equals, because for C equals 1, this is the solution of the equation. So in other words, nice generalization of the MM1 solution to the problem. The proof is relatively straightforward once we've shown this first result, that this particular function is monotonic in beta. Now that takes a little bit of work, and eventually you get a circular argument that allows you to prove that it must be so. Once you have that this expression is monotonic, that means that this expression is simply between the two values of the expression itself. So f is that expression, and we can show that f of 0 is equal to that, and that the limit of f of beta is equal to this. And then it can be shown furthermore well, it's pretty obvious here that this is actually less than 1 over mu, and it can be shown that that enumerator there is less than 1, so that the whole thing is less than mu. It takes a little bit of work, but it's relatively straightforward. So now, if we go back to our original problems, we're going to leave that little interesting fact that the solution to that equation is almost linear. And we consider our two hospital model, so we now have 2 hospitals. We're going to allow these hospitals to interact via a routing game. So everything is going to be the same, except that the emergency vehicles are going to equalize the flow at both hospitals. In other words, they're going to share out the demand of patients in such a way that the weight at both hospitals is the same. Now this is a very simple example. I've taken some data from local hospitals here in Cardiff and very, very vaguely extrapolated to get two hospitals. It's not meant at all to be a representation of the actual hospitals at Cardiff. And what we've had is, okay, let's say that the hospitals have 2 strategies. Either to put the lowest amount of beds they can in the emergency unit, which is 1, or to put the maximum amount of emergency units they could put in. So this hospital's got 1,080 beds, so it could put 1,079 beds in the emergency unit. And vice versa, this hospital has 480 beds. So it's got the same. Now in this particular case, we see that if both hospitals put 1 bed in the emergency unit, that the total throughput is quite low. And then if the second hospital decided to react to this and increase the number of beds, then it would get a lot more throughput. So it would increase or deviate to this strategy. But then if we're here, the first hospital would deviate to this strategy. And this is in fact a Nash equilibria for this very simple game. And very interestingly, it's also the optimal throughput. But of course, these 2 strategy sets, so having having almost none or almost all of your beds in the emergency unit, isn't very realistic. So if we take a look at this little game here, the first hospital can put between 35 and 36 beds, the second hospital between 28 and 29. The numbers are quite small, the differences are quite negligible, but if we look carefully, should be able to see that this is an equilibria. If we were here, then the second hospital would benefit from deviating to here, and if we're here, the first hospital would benefit from deviating to here. And then once we're there, no hospital can benefit from deviating. It's in fact a prisoner's dilemma, because very interestingly, the optimal throughput is up here. And so now, in other words, the optimal throughput, the sum of the 2 throughputs, is indeed bigger than here. So what we're going to measure is called the price of anarchy. So it's in these games when you take the ratio of the Nash cost over the optimal cost. As here, we're actually trying to maximize the numbers, we take the inverse of that ratio. And we get a very slight price of anarchy. The price of anarchy will always be bigger than 1, bigger or equal to 1. But here we have 0.2% worse performance due to selfish behavior. Now what we're going to do is investigate this a bit more. So some technical details. All this work was done using open source software. The first step was to solve the routing game for all strategy pairs. So in other words, for every single possible scenario, every hospital choosing a particular action, solve the routing game, in other words, decide how the emergency medical vehicles would share the patient flow. Whilst we were doing that, we'd identify the optimal strategy pair, to simply find the total best sum. And then what this actually does is create a bimatrix, and we solve the bimatrix game using the LRS Nash algorithm. I'll put a link to that at the bottom of this video. And then finally, we just compute a POA. So almost everything was done within Sage, which is a great open source mass package that's a wrapper for a lot of Python programs and other things. But we solved the bimatrix game using LRS Nash. Here's 3 contour plots that show the total throughput for both hospitals. And so what we see here is for the first hospital that its optimal throughput is there, but if the second hospital happened to choose to have 400 beds in its emergency unit, then in fact the first hospital's optimal would be around here. So it would have to react aggressively to the second hospital. We see similar things for the second hospital, but interestingly, this thing's in the way, but the optimal throughput is around here somewhere for both hospitals. So that's just the sum of the two outputs. And here's the strategy distribution. So what we have in red and blue there are the optimal strategies here. And then of course these are pure strategies, and they're quite low. And then what we have in blue and pink are the strategy distribution at Nash equilibria. So for this particular game, if we consider the entire strategies, there wasn't a pure strategy equilibria. It was a mixed strategy equilibria, which obviously adds to the complexity of finding the solutions to these games. And what we're seeing here is that whilst they should be around the 50 bed mark, both hospitals should be around the 50 bed mark, well actually the second hospital is at the 25 bed mark. At Nash equilibria, we're starting to use sometimes even up to 500 beds for the first hospital. Okay, the second hospital sometimes behaves, but a lot of the time we're using, so in other words, both hospitals are trying to get more patients through because that's what they're trying to maximize. And that causes a deficit to the entire system. Now this particular graph, and the previous graph, these here, they were obtained by truncating the strategy sets of the hospitals by 50. So it's again not very realistic. But it was simply because of the size of the problem. The biomatrix solver took a while as it was. And so what I decided to do was to investigate a bit more. So this is the original biomatrix, which is very, very big. And I thought, well, by initial investigation, you could see about where the strategies should be. And so we're saying that the first bed, for example, will use something between 30 and 50 beds. Sorry, the first hospital will use something at 30 and 50. And the second hospital will use something between 20 and 40. Did a second experiment where we allowed the second hospital to go between 25 and 45. And a third experiment where we used between 35 and 55. Here's an example of the output. So looking at allowing the first hospital to choose between 30 and 50 beds and the second hospital to choose between 25 and 45 beds. We see that the first hospital's optimal output is down here. So the more beds the better, basically. And the second hospital's optimal output is somewhere around here. Between 30 and 37 beds. Now, what's interesting is that the optimal is around here. So with the second hospital using less than it should, as well as the first hospital using less than it, sorry, not that it should, less than it would, if it was acting selfishly. Here's a graph of the probability distribution. So again, we have the optimal strategies are right there. And then we have the Nash strategies. And so first of all, you see that there are only two strategies that are being mixed here. And we see, for example, that the first hospital, okay, will sometimes, quite often, use the correct amount. But every now and then, the strategy distribution says that it should use much higher distribution of much higher number of beds. So again, trying to drag a few more patients through. And similarly for the second hospital. So going back to the price of anarchy is to seeing how bad is this effect. And so what we have here is as we increase the demand on the emergency unit, so increasing that demand, how does this affect the price of anarchy? Which, recall, is just a ratio of how bad selfish behavior is. And so we plotted this for various, for all three strategy sets. And so the demand coefficient is the amount by which I decided to increase the demand. So 1 is the actual base demand. We see it has quite a high price of anarchy, almost a 4% decrease in performance. When the demand's quite low, the price of anarchy is quite low. That's simply because there's not much leeway to go wrong. And then when the demand gets quite high, the price of anarchy comes down. And this is because there's not much leeway to get things right. In other words, here the situation is bad. Because the system can't cope with the demand. So it's bad either way, is basically the way to understand this. And so that's interesting. So that seems to show that the effect of the demand increases the price of anarchy. Another approach is to look at the effect of P. Now, if you don't recall what P was, it is the percentage of patients that are admitted from the emergency department into the ward. And so as P increases, so does the price of anarchy. Sorry, not admitted. P is the percentage of patients that are not admitted, so that leave the ward. So leave the emergency department, never enter the ward. So as P increases, we are in effect increasing the importance of the emergency department as to the total throughput. And we see again that the price of anarchy increases. So this leads to an interesting consideration. That in real life, is there any times, looking at the data, are there any times where the importance of the emergency unit does increase? So perhaps not by increasing P, but just by looking at the effect of day of the week. 0 is just the mean, so that's the data we've been playing with previously. 6 here is Saturday. So straight away you see an extremely high price of anarchy. In fact, up to 20% less performance. So price of anarchy of 1.2. And that is simply due to the fact that on Saturdays the amount of elective patients coming in goes down, and the amount of emergency patients coming in goes up. So that's certainly not a negligible effect of selfish behavior. To conclude this work, I've shown you two things. Firstly, an approximation formula for solving this equation, which I think is very interesting. There's potential to be used. And secondly, a biomatrix game consideration of hospital interaction. Now, all this work fits on an extremely simplistic model of a hospital, so I immediately acknowledge the weakness there. But despite that, I've shown that selfish behavior when trying to optimize throughput is indeed not negligible. So just by optimizing a single hospital, and if you remember that little cartoon at the beginning where I was giving the hospital a new lick of paint, optimizing a single hospital could perhaps have a negative effect on the entire system. And so it's very, very important when thinking about this sort of work to consider a whole systems approach. And that's everything. So at this point, I would invite questions.